Hey everybody, I forgot to record today's discussion in intensive physics, so forgive me about that, but I'm making a video now to go over what you missed. So I started off by asking students, first of all, we looked at, reminded ourselves of the universal gravity equation, G m1 m2 over r squared, and if you remember, one mass we call m1, or if one mass is particularly big, you can make it be a capital M, and then another mass, you can call that m2, or if it's a smaller mass, you can make it be a smaller m. That is what m1 and m2 are. G is a very tiny number, it's a gravitational constant, and then r is the distance between their centers, and this is what students reminded me today about and what the equation is, and you've worked some of these problems. So what I asked them to do, and we broke off into groups, and I asked them to imagine that you and somebody else are eating dinner together, and just, it doesn't really matter what the masses are and what the distances are, but make it realistic. So imagine you've got a big person and a small person. It's kind of helpful to think about two different size masses. So here's my little Lego scuba diver, and then Shmi from Disney's Captain Hook and Peter Pan. And so imagine these guys here are eating dinner together, and maybe Shmi put on a little weight, and so we might think that his mass, that big M, is 100 kilograms, say, and he's eating with the smallish person, and say that little mass, and everybody had different values, but we can say something like 50 kilograms just to make it simple. Okay. And then they're eating together, and this is not during the coronavirus, we imagine, so they're not sitting 4 or 5 meters apart, but rather maybe they're sitting, who knows, R is 0.75 meters, and you can decide if it's half a meter or 2 meters or something like that, but they're eating in close proximity. And then I sent them off into little rooms to calculate what the force of gravity is between the two masses. Okay, so do that now, and while you're thinking about it, I'm going to draw the big mass here, Shmi. Okay, and I'm going to draw the little mass over here, this little guy. Okay, and this fella here, the big guy, feels the little guy pulling him. Okay, and I'm going to call that the force of gravity. I'll call that F1, and then the little guy feels a force of gravity pulling this way. I'm going to call that F2. All right. So of course, if you do the calculations, we see that F1 is going to equal G times big M times little m over r squared, where r is the distance between them. And that, of course, is going to be exactly the same thing as F2. And of course, this is the universal part of the universal law of gravity, is that the two masses feel equal forces. F1 is equal to F2 because what in this equation is different from this mass to this mass. And we'll talk about what that means here in just a minute. Okay? And so if you do the calculation, and hopefully you plugged in G into your calculator. All right, so we did that in another video, in another class. So alpha G, and just to make sure it's working, I'm going to do alpha G and hit enter, and lo and behold, there it is. And that G is the same as that G there. Okay, so I'm going to do that again, alpha G, and then big M is 100 times little m is 50, and then you divide by 0.75, and what a lot of people forget is to square that. So 0.75 squared, you probably can't see that, sorry. And also, a lot of people don't know you can just multiply a constant times a number. You do not have to put in the times symbol there, although you can, it doesn't hurt. Okay, and so we end up seeing that this is about 6 times 10 to the minus 7, and then the units, if we put everything in kilograms and everything is in is in meters. This is going to be about 6 times 10 to the minus 7 newtons. Okay. And then I asked them in their rooms to tell me which one was bigger, and of course the forces are the same on both. And then I asked them to tell me why, when you eat dinner, you and your dinner guest, why don't you slowly move together? Because there is a force acting on you, even though it's small, it's not zero. And why don't you slide in together? And they had some thoughts about that. But primarily, it's because of friction. The force of friction is going to be much, much bigger than this. And so we played a little game there, and we asked, what is a really, really tiny coefficient of static friction? And people said something like 0.02. That would be a very, very low friction environment. And so then if we wanted to figure out what the force of friction was, if this thing were pulling on it like so, right, what would be the maximum force that would make this guy start to move? And of course, the force of friction is mu times the normal. So let's take the tiny guy just to make it be the smallest friction possible. 0.02. The normal force when he's just sitting down and eating dinner is his mass, which is 50 kilograms, times gravity, 9.80 meters per second squared. Okay. And then when we do that calculation, 0.02 times 50 times 9.8, we see that it is a force of 9.8 newtons. Okay, and that is, quite large compared to that. In fact, it's humongous. This does not mean it's 7 times smaller, or this is 7 times bigger. It means it's 7 orders of magnitude bigger. Actually, this is closer to 8 orders of magnitude, because this is close to 10. So 8 orders of magnitude bigger, which is why gravity, we don't even consider gravity in any of these calculations. However, if they were in space and the force of friction is 0, right, there's nothing slowing them down, in space they would actually come together and they would hit. We can't solve this problem in this class because we don't have the calculus, but you can see here that as the objects move closer together, the R gets smaller, and so the force is going to get bigger. Okay, and as the force gets bigger, they're going to move together more and more quickly, and at the end they're going to start moving faster and faster. Not only that, but they're also moving. They're not starting from rest, and so we have the kinematics to deal with. But you have to wait until AP Physics to handle that because of the changing acceleration. So now that we see that the two forces acting on both masses are equal, the next question is, does that mean that they, if they were to move toward each other, does that mean that they would move with the same speeds? Would they meet in the middle? If they start on the opposite sides, would they meet in the middle? Would they reach there at the same time? Would they reach, would they be traveling the same speed? Things like that. And even though it's tempting to say that they would travel the same speed because the forces on them are equal, that is true. The fact of the matter is that the smallest object is going to accelerate more quickly. Okay, and we can see that if we set up, Newton's law. Let's take for example the little tiny mass here. Okay, so he's being pulled one way or the other, but if we add up all of the forces acting on that little mass, it is the mass that's doing the moving times the acceleration. And there's only one force acting if we're in space, right? If we're in space, there's only one force acting. That would be the force of gravity. Okay, and so that's going to be my 6 times 10 to the minus 7 newtons. And that's going to be the same for both masses, right? We talked about that. That's going to equal MA. And I'm going to call it MA2. If you want, we can label this as 1 and 2, MA2. Okay. And so we can see that A2 is equal to the force of gravity divided by the little mass, M2. And if we apply the same thing to the big mass, we would see that A1 is equal to the force of gravity, which is the same number, but this one is going to be divided by the big mass. m1. And so whichever mass is biggest, the acceleration is smallest. Acceleration has an inverse relationship with mass. And so this is why if these guys were literally in space, floating around, Smee would move, but so would the little guy. And in fact, the little guy would move more, and they would hit, somewhere over here. Okay? And again, this is a problem that we cannot solve in this class because we don't have the calculus. We don't see how the acceleration is going to change. This is a very typical calculus type problem. But the initial acceleration, this is really the initial acceleration of both masses. The little guy is going to have a much bigger initial acceleration than the big guy. Okay? And this is Newton's big aha moment, right? When Newton was sitting around and he was thinking about apples falling, and again, Newton did not think, I've discovered gravity, I've discovered that apples fall. No, I mean, people have known that for millennia, right? But what he discovered, again, is that not only does the little mass fall in a big way, right? And so the force of gravity pulls the apple down. The acceleration of the apple is 9.8 meters per second squared near the Earth. The idea that he came up with, the big aha moment, was not only does the apple fall, but the Earth rises. This force of gravity acting on the apple is the same as the force of gravity acting on the Earth or the planet. However, the acceleration of the Earth is microscopically small, and it's approximately 0. It's not exactly 0, though, and that's the idea, is that as the apple falls, the Earth, as the little tiny apple falls, the big Earth rises to meet the apple. Okay? Again, it's not much. You can't detect it because the apple's so tiny and the Earth is so big. That said, as the moon pulls the Earth pulls the moon, or as the Earth pulls the moon pulls the Earth, and you can actually see the little wobble of the Earth as it goes around the sun, and that's due to the effect of the moon's gravity. Okay, so that's that, and then we talked a little bit about astrology, which is not something that I necessarily believe in, right? In fact, I don't believe in it at all. It's not astronomy. Astrology, people will say, it's, people who believe in it, is based on scientific facts, and that is true, right? And that if you were born, and here's the sun, and here's the Earth, okay, and let's say a baby is born here, whatever, if you draw a line between the sun and the Earth, and you keep going out into space, it's going to hit some constellation out here, okay? And let's say that constellation is Sagittarius, which is what I am, right? So Sagittarius, I was born in December. So here this line through the sun means that the sun is in Sagittarius, and that is my zodiac sign. That's my sign. That's my horoscope, whatever. And what it means is, or what people think it means is that the stars, the minute that I was born, and all the heavenly bodies are pulling on my body, the gravity of those stars are pulling on my body when I was born, that it sets my personality, okay? And therefore Sagittariuses and Tauruses can't marry each other, or they can't be friends because I don't know, it's just silliness, but the idea is that the gravity of these planets that surround the Earth and the gravity of the stars are pulling on the baby in utero, and it's changing the personality of the baby. It's a lot of hooey. But, so let's prove it. For example, let's don't even think about stars that are light years away. Let's think about the nearest planet here. Let's think about maybe Mars. How does Mars pull on that baby? Okay? So here the Earth is orbiting the sun. I should have drawn that circle smaller. Sorry. The Earth is orbiting the sun, and then Mars is orbiting the sun. Forgive my drawings here. And so the baby's born on Earth. One of the questions that students had is, do we have to consider the radius of each planet when we have to do these calculations. And if we look at the equation sheet here, okay, so here is Earth's mass and Mars's mass, and there's Earth's mean radius, about 6 million meters, and Mars is about half that size, 3 or so million meters, and that's pretty big, but 10 to the 6 million. If we look at the distance between the planets and the Sun, it's 10 to the 11 meters. So this is 5 orders of magnitude, almost 5 orders of magnitude. This distance between, the Sun and the Earth, call that RE, that is about 1.5 times 10 to the 11 meters. And the distance between the Sun and Mars is about 2.3 times 10 to the 11 meters. We'll call that RM. And those distances are huge compared to these little distances. In fact, if I were to draw this to scale, I wouldn't be able to use this pen because this dot is not 10,000 times smaller than that distance there. You wouldn't be able to see the dot. So it's not drawn to scale. So the idea, again, is I want to know what is the effect of Mars's mass acting on the baby who's born on Earth. Okay, and we'll even make it be the closest possible distance here. All right, and so when Mars is here next to the Earth, this is called perihelion. And then when Mars travels to the opposite side, right, when the Earth and Mars are in opposition, okay, this is called conjunction and opposition, then this is aphelion. Okay. So this distance is small, and this distance is quite large, much, much larger. Okay, and if we remind ourselves of the equation, right, that r squared term is going to have a tremendous impact. All right, so let's do it. Let's figure out what is the force of gravity acting on the baby, okay, due to Mars. And let's say the baby, let's say the baby is, I don't know, 2 kilograms, something like that, okay. And we need to calculate what this radius is. I'll let you be thinking about that as I continue to talk about the problem. So here, this is going to be G times the mass of one object, the mass of the baby, times the mass of the big object, or the second object, the mass of Mars, divided by r squared. And again, this is r. It's the distance between their two centers. So what is r? R is going to be the radius, the orbital radius of Mars minus the orbital radius of Earth. Convince yourself that this distance minus this distance is that distance. All right, and so if we just type it in, so let's see here, the orbital distance of Mars is this guy here, 2.28. Again, we're doing scientific notation to the 11th minus 1.496. Scientific notation to the 11th. Okay, hit enter. And so R is 7.84 times 10 to the 10 meters. Okay, so forgive me for not writing this down. I'm just trying to be quick because I'm running out of time here. If I were to then type this into the calculator, I would have alpha G times the mass of Mars, right, which is, or mass of the baby, which is 2 kilograms, times the mass of Mars, and so the mass of Mars is 6.42. Again, scientific notation to the 23rd, divided by our answer here, our radius. I'm just going to do second answer, and I want to square that. Don't forget to square it, and then boom. So I see that this is 1.4 or so times 10 to the minus 8 newtons. So if we consider the effect that the planet, a huge planet, and fairly close as far as astronomical distances are concerned, very close proximity to the baby when it's born, it is a much smaller force than the force of gravity between two people, right? And so the doctor, delivering the baby, she is pulling on the baby with more force than the heavenly bodies are. That is something to consider when you read your horoscope. And listen, don't get me wrong, I love horoscopes. I think they're hilarious. I think they're fun. Just like I love Marvel hero movies, right? I know it's not real, but yet it's still fun to think about. But the problem is, of course, if you start to think that they're rooted in science, and therefore that they're to be believed, just because there's a nugget of science in astrology doesn't mean that that is to be believed. Certainly not by my physics students. And I'm sure that comment's going to get a lot of traction, perhaps on the interwebs. So bring it on. So what I want to do now is let's discuss what happens if you have more than two masses. The universal law of gravity says that tells you what the force of gravity is between two masses. So what if you have three, for example? What if you have, little guy here eating next to the big guy here, next to a smaller tanuki here? Okay, and so we have three masses, and this is I'm gonna call this M1, and M2 is gonna be tiny, and M3 is gonna be this really big guy. I can make them bigger. M3. Okay. And so how do these three interact? And so what we have to do is consider one at a time. For example, we take the little tanuki doll here. If we want to look at how this guy is being affected by these two, you have to do it in two steps. And so it's a superposition principle. It is, this little guy is attracted to the little scuba diver. Okay, and so that I would label he's being pulled to the right, and so that would be the force of mass 2. Okay, and we don't know the masses and we don't know the distances, but let's represent it like that. He's also being attracted to the big guy, M3. Now the big guy has more mass, so you may think that his force that the little tanuki is experiencing is going to be a bigger force because this guy is so much bigger than the scuba diver. But his distance is so much greater. And so it's possible that the little guy here could have a greater force than Smee does. And in fact, it probably will be will be likely to be that way. And I'm going to call that F3, which is the force of the first mass the force on the first mass by the third mass. And so together, when you add them up, this is M1, when you add them up, they're going to both be pulling to the left, and so there's the distance of F2, and then there's the distance of F3, and so that would be the net force acting on M1. And so all forces will pull him to the right. If we take a look at this little guy here, then he is going to be pulled to the left, right? Being attracted to the tanuki doll, and so that is going to be a force that we're going to call F1. And if you recall, F1 and F2 have to be the same, right? Because this is the universal law. If 1 pulls on 2, then 2 pulls on 1 with the same amount. Now here, this guy is going to be pulling on him, and if we put him right in the very center, then he's going to pull with a force that's much greater than F1. And I'm going to call that F3. Okay, and this force is going to be greater because his mass is the same, or his mass is bigger rather, but the distances are approximately the same. And so when we analyze the net force acting on the second mass, we're going to again add them, but this one is going to be a negative because it's going to the left, and this one will be positive. So it's going to be this distance minus that distance ultimately, and you're going to end up with a net force like that. And then finally, we could do the same thing here for the big mass, M3, and he's going to be pulled to the left with F3. F1. It's going to be the same size as F3, and he's going to be pulled to the left with F2, which is going to be the same size as F3. And so when you add them up sorry, I should have put those vectors there. When you add those up, it's going to be pulled like so. Okay, so depending on the masses and the distances, these forces here will add up. But again, it's a superposition principle. You're just summing all the forces acting on each mass. Finally, if we have a situation like this, where the masses are not in a line, they're not collinear, but rather they're spaced out like so. So I would have my M1, my M2, and my M3. Okay, and we want to look at the force acting on this center mass here. Well, we see that M3 is going to pull him this way, and M1 is going to pull him this way. Okay, so which way will this the center mass, or this mass here at the origin, feel a force? Well, he's going to feel it again, just like we did up here where we add the vectors, but here we're adding them, we have to add them vectorially, just like we did here. It's just easier when it's on a one-dimensional graph. So here when we add them vectorially, again we get Pythagoras, and that would be the net force. So this little guy would move like so, but then of course as he moves the distances are changing, and so he would then do some kind of weird motion, and maybe he starts to orbit one or both of the masses, and you can get into some really cool orbital mechanics and numerical methods and things like that. But that's beyond the scope of this class. I just wanted to show you how to handle more than two masses.